Hello everyone. I hope you're doing fine and having a great time. Welcome to the second last lecture of this course, Fundamentals of Plastic Deformation. You would be generally already familiar with the overall outlines and what we have done. So today I am also trying to play with this new technology of making these sessions more interactive. So I would like to use a lot of pen today for discussions and details. Anyways, so what we have done until now is we have summed up this part 1 where we talked about independent basics. In the last few lectures we already talked a lot about process dependent basics on everything, and last topic was flow curves. Before that I talked about tensile tests, and we get flow curves from tensile tests, and Dr. Irani talked a lot about the flow curves and how we can model them and different methodologies and techniques and empirical models and so on. And today we are in this part 3 where we want to use that all previous knowledge to build up on the actual physical processes, for example, such as flat longitudinal rolling, and this is something which we will talk a lot about today. Generally, when we define rolling, this is something which we have already discussed, we have already studied in the lecture before, but just to repeat, the forming process, it is a forming process with direct pressure effect, the rolling process, continuous forging process between rotating rollers, and continuous upsetting between arched and rotating pressed surfaces. Generally it is separated in 3 types of rolling, so longitudinal rolling, cross rolling, and skew rolling. You can see all the schematics down here. You can read a lot about the rolling process and its types and how it is classified in the books which are already shared with you. Generally we divide rolling in 2 steps. So one is flat rolling and the other one is profile rolling. The flat rolling process is something in which we are only getting a flat profile, and then in profile rolling we convert it into a certain shape. They can further be classified in several categories which are listed here. So just to give you a general background of what rolling is. Before I go into the details, I would like to go back to the basics. We will see the video which we already have seen once before, but now with a different aspect or perspective, because we would like to do a lot of calculations and understand the basic function of the plastic deformation phenomena which we have studied in this context and how we can use all that knowledge here. But before that I would like to share this video with you all, so you can make a sense out of it, or it will help you understand how things are happening. Let me do it again, and while doing that I would like to share the audio as well. Okay, and probably I will not be able to record this in the recording, but anyways, when I will be playing the video, please inform me if you are able to listen to the audio. Okay, super. Wait, no, yes. So I hope you found it quite interesting. The process which is shown in the video was multi-stage flat rolling, and it was at higher temperatures, which is a relatively complex process because we have to also care for the temperatures and the speeds between the rolls. But generally, yeah, we break it down into a smaller piece, as you can see it on the slide. I hope until now things are clear. So what is happening is that we have rolls which are rotating in the direction of rolling. Depending on the type of the rolling, they can change their direction and so on, but here we will focus on only a singular process in which the sheet is coming from left side, so from here, and going out in this direction. Now instead of using T, I would like to use height, so this can be H0 and this can be HF. In this process, when we have this block here which we want to roll in the final direction, now we would like to perform some calculations by simplifying it. It is a very interesting example of bulk deformation processes where the process is complex enough to understand how things are getting along, and simple enough so that we can make some calculations by hand and by assuming a few things. Now this is a 2D map, but of course this has a third dimension, which is thickness, so it would be in this direction as well, so on. And then this would be the width of the material, and then before rolling the length of the billet will be L0, and then after rolling the length of the billet will be final length. And of course when we are rolling it, we are reducing the height, so the length of the sheet or the billet will increase during rolling process. But considering the constant volumetric law of constant volume, we will have fixed volume on both ends. So we can start with initial length multiplied by initial width multiplied by initial height is equals to final length multiplied by final width multiplied by final height. Okay, so which means that initial volume is equals to final volume, and these are the terms which are explaining it. I hope it's clear until now, because after this it will speed up into something else. Now assuming that the width of the billet is kept fixed, as you saw in the video, so we use some side rollers to keep the width of the sheet fixed. So generally when the initial width is equal to final width, we can cancel these terms out. So what we have is length and height is equals to length height, and then basically I can divide both terms with time, and then this initial length divided by time, and then this final length divided by time, we can write it as this is initial velocity, height, and then HF. Let me change the color now. So until now it is quite clear and understandable that we have this initial velocity, which is this, and then we have final velocity of which is this. And the fact that this height is bigger and this height is smaller, in this case, let's use pen with green. Okay, so we now know that this is smaller and this is larger. To keep this equation homogeneous, then this should be larger and this should be smaller. Is it clear? So I'm just making a poll just to make sure that everybody is on the same page. Until now, everything is understandable. Yes or no? Quite simple, very simple equations. Super. So the response is positive, which is great. Okay. Now, this means that if we change this equality sign, so almost all the people who polled said yes. Super. So this means that if we change this sign, this is larger. So let me change it back to red. So this means that I will write it like this. So Vf is greater than V naught. This means that this velocity here, the outlet velocity, is larger than this initial velocity. Interestingly, that means, let me change the color, that means that the material here has a different velocity than the material here. So the velocity between these 2 points is changing, it is not fixed. And then we have another thing, which is velocity of the roller. So how do we define that? You see here Vr, but the rollers are rotating, so it will have an angular velocity. So this means that Vr, I'll write capital R because I don't want to confuse it with this. So this is velocity of the roller is equals to radius of the roller. Here we call it capital R, so let me write it in capital R, R omega R. So the angular velocity multiplied by radius of the roller is Vr, and this velocity is fixed. And usually always in rolling process, so what happens is that this rolling velocity is greater than initial velocity of the billet, but is less than the final velocity. So this means that here, let me I don't know, can I zoom in? I don't know. No, I can't. In the next slides we will see how, but generally this means that the velocity here is slow, but the roll is let me change it. This means that the velocity of the billet here is slow, but the roller is moving fast. And in the middle there would be a point where the billet and the roller will be moving with a similar velocity, just a point here, and then after that the billet is moving faster and the roller is moving slower. So this factor would create a positive friction coefficient, and this factor would create a negative friction coefficient here. And that is something which plays a very important role in the rolling process, and we want to further analyze that. Apart from that, we will come back to it quickly. The process of rolling is not always flat, so there is always a bending force, which you can see here. Flat rolling is not so flat. It has its own issues as stated in this slide, but we are not going to discuss them in detail. Rather, we will focus on the ideal rolling process. So because of this bending, we have fixed roller from these ends, but it is exerting a consistent force here on the sheet. So we have buckling in the roller, which we can see here, and this disrupts the overall profile of the sheet which is being rolled, and therefore we get this kind of phenomena which we have to control by adjusting the forces and overall effects. So we are not going to analyze this, but this also comes into effect. This is something which we discussed before in the previous slide. So there is a non-slip point, and before this non-slip point there is a backward slip. So the material coming in is slower than the roller, so we call it a backward slip, and after the neutral line the material moving forward is faster and the roller is slower, so we call it a forward slip. And to make this process continuous, the value of the force here in the area before the neutral line should always be higher than the force which is here, and this is affected by the friction coefficient. But generally, if you look at the profile here, we see that the pressed length from maximum to zero from so if I plot this from this point, so from point 1 to point 2 is plotted here, and we see that during rolling the strain in the material, let me make it bigger, the strain in the material is constantly increasing and is getting asymptotically straight line, because after this point it will deform, it will not deform at all, and whereas the strain rate is decreasing exponentially. We see this here. So here the strain rate would be much higher and slowly it will reduce. And this is generally the overall behavior, that now you see that there is a backward slip and there is a forward slip. And if I come to this point of calculating the forces, we see that at this point on the roller, we are experiencing a force which is this one, which is rolling force. It is mentioned here as Fr, and I couldn't get Vf. Vf is greater than Vr is greater than V naught. Could you please repeat it? It is quite simple. I will do it here. So, or in the previous slide. So here, this is a no slip point, which means that velocity of the roller is equal to velocity of the billet. Velocity of the billet here at this point. But before this, because it has a certain V naught initial velocity and this has certain Vf final velocity, this initial velocity is slower than the velocity of the roller here, and this final velocity is higher than the velocity here. And that is how the rolling process goes on, because this is fixed but this is slower and this is faster. So I don't know how to explain it appropriately, but generally from the set of equations which we solved here, we can see that this should be higher than this one, no? But then there is a roller velocity which is fixed. So between these 2 points there comes a point where these 2 velocities are same, and after that they're different. So generally stating the rule, which is this, so the final velocity is highest, then there comes the rolling velocity, and then there comes the initial velocity. If you still do not understand it, we can discuss it at the end. But okay, so now when we are talking about the initial point, which the first end of the rolling, which is responsible for carrying out the rolling process, we see that there is a force. We are calling it Fr, which is rolling force, and this can be divided in two components, a horizontal component and a vertical component. And basically the vertical component plays a role in, so it can be divided in two components. If I make this here, let me do it again. So this component can be divided in two components. So horizontal one and vertical one. This horizontal component is responsible for rolling, and this vertical component is responsible for compression. Or I can say that this horizontal component is responsible for pulling the sheet through. And this component is stated here. And from the laws of trigonometry, we see that this component is Fr cos of alpha. And when I want to calculate it, we have a horizontal component of friction force, which we are stating as this, and it is also equal to mu Fn cos of alpha, where mu is the friction coefficient. So generally, doing a little bit of arithmetic, we come to this conclusion. So if we want to have a grab condition here, the friction coefficient should always be higher than this condition, so tan of alpha. And this alpha is basically this angle, which is angle of, we call it grab angle or roll angle. So you will find different names for it, which is basically between the first point of contact to the final point of contact. The angle between these 2 points is called alpha. And then, for example, we see that our friction or rolling condition is basically majorly depending on this friction coefficient. And this friction coefficient then in reverse is depending on other forces and radius of the roller and so on. So generally we would like to see how this friction coefficient is affected. So this friction coefficient mu depends on the following conditions. It is depending on the lubrication during the process. It is depending on the working material. So if we are lubricating it, the friction coefficient would be lower. If we are keeping the surfaces rough, the lubrication there is less lubrication, then the friction coefficient would be higher. The working material, so if we are changing the material, for example steel, aluminum, copper, magnesium, in each material case the lubrication coefficient would be, the friction coefficient would be different. And one of the major things which the friction coefficient depends on is temperature. So temperature plays quite a huge role in defining the friction coefficient. And for example, if we are keeping the material fixed, so let's say we always want to roll steel, and we are keeping the lubrication condition fixed, so let's say we are using water to keep our rolls cooled, or some coolant lubricant to keep our rollers cool and keep the process smooth, then temperature is the only thing which would be controlling our friction coefficient. And the values of friction coefficient for different temperatures vary significantly. For example, for cold rolling conditions, the friction coefficient usually is between is nearly 0.1. And this friction coefficient is a physical property, so it depends on the material and the surface condition, so we cannot really define it or state it. For warm rolling conditions, the friction coefficient is around 0.2, and for hot rolling conditions it is generally 0.4, but can be as high as 0.7, because at higher temperatures there is a phenomena in which the material temporarily welds with the roller surface, and we call this phenomena sticking. So in hot rolling conditions, usually we have a friction coefficient around 0.4 and 0.5, and 0.4 and 0.5, and then it can be as high as 0.7. Now when we have stated this, what I would like to move towards is I would like to move towards some of the basic set of equations which we can use, a simplified set of equations which we can use to calculate certain things. There's a question: what is the difference between grabbing condition and pull-through condition? I don't know. Grabbing condition is when the friction coefficient is higher than the required coefficient, so we would be able to do the rolling process. I'm not sure about the pull-through condition, sorry. Anyways, coming back to the lecture, so considering this simple process of rolling, where we initially now have initial height of the billet, final height of the billet, initial velocity, and the final velocities, we can do some simple arithmetic to calculate these. So angle of grab, this is important. This is this alpha, which we can calculate by using any of these simple equations, and generally it is basically the difference in height divided by the roll radius, and then we can get this alpha. But remember, when we are getting this alpha, this is from, if we keep the units appropriate, this is always in radians, so it will not be in degrees, it will be in radians. So either you convert it into degrees if you want to continue with further calculations, or what you can do is you can do further calculations by computing everything in radians rather than in degrees. The next thing which is important is rolling angle. What is the difference between angle of grab and rolling angle? So angle of grab is this whole angle from this initial point to this final point, whereas this rolling angle is angle from this initial point to anywhere we want to calculate it. So it can be calculated to any infinitesimally small point, so therefore we will see this h minus h1 condition here, and then we can calculate the total height reduction, which is simple, and so on and so on. We are assuming that the width is fixed. Then what we are interested in knowing also is overall area which is pressed. So this would come under this category of height versus width. So this is where that would come in. So here it is mentioned as breadth. Let me do this. So this is length and this is width. What does grab mean in this context? In what context? We are calling this grab length, so the length of the billet which is between the rollers, which is in direct contact with the roll surfaces, we are calling it grab length, which is mentioned here as LD. And then this angle from the middle of the roll to the initial arc and the final arc length, we are calling this grab angle. So this is what grab means in this context. I hope it is clarified. And then you already have an idea of how do we calculate strain. So here it is calculated as logarithmic strain. We can calculate its largest value. So this would mean that the total strain, we can calculate its instantaneous value, which would mean anywhere at this point what is the strain, and then we can calculate its average value. So what is the average strain throughout this deformation? And generally when we are talking about the strain, we are talking usually about this value here. Let me clear this up and highlight this. So this means that the true strain. And you already know that for this corresponding true strain, we have a corresponding true stress value in the flow curves, which we can extract to know that how much force is required or how much stress is required to achieve that force, and so on. And then there is equivalent degree of deformation, which the equations are given here for calculation. Let's not go in detail there. I am quickly skipping through the slides where all the general formulas are given, because they are generally provided for a lot of values, for calculating instantaneous values, for calculating maximum values, for calculating average values. But I'm just skimming through to move towards the overall challenge which we want to solve using these methods and techniques. And then we have this circumferential velocity, which is velocity of the roller, which we already discussed, which is omega r. And from here we can also correlate the linear velocity of the rollers and the angular velocity of the rollers. Please note that this is in radians and not in degrees. These are the calculations which we have already performed. And from here we can get the velocities and the instantaneous velocity and so on. And from these velocities we can calculate the forward slip and the reverse slip, which is quite simple to understand, but relatively tricky. For example, in the case of forward slip, which is here after the neutral point. Let me do it again. So if I am constructing it a little bigger, in any case, so if this is a neutral point, we have forward slip here and reverse slip here. And there are simple formulas given to calculate these, which are provided here. And then there are other methods which have correction factors given by people, which we can use to calculate it in more detail and more accurately with certain conditions and so on. Yeah, and then same goes for and then there are formulas for strain rate and mean strain rate and so on, which we don't want to talk about, and we directly want to reach at this point here. Now what I've done is I have uploaded these slides in the Opal course, which you can already find. The problem is simple, which we want to solve here, which is that we have an initial height of the billet, which is 20 millimeters, and we want to roll it down to final height of the billet, which is 10 millimeters. And while doing that, we want to keep the conditions of worm rolling. And now you know that during worm rolling, we can reach a maximum friction coefficient of 0.2. Considering that, what I would like to do is, if this is a symmetric process, so these both rollers have equal roll diameters, what I would like to do is I would like you to calculate this radius. Okay, anyways, I would like you to calculate radius of the roller, which is appropriate for doing this process. Just for a hint, what we can do is we can do some calculations together, but in the end I would like you to calculate this, because interestingly this is a question from last year's examinations, and what I observed was that there were many students who were attempting the examination, but almost none of them attempted this, which was interesting for us, that why didn't nobody do it when it was quite easy to get so many marks out of this very simple calculation. To do that, what you can do is you can use the formulas which are previously given on the previous slides. It is no. Okay, to do this, what we can do is now okay, there is a very simple formula. So what we do is initially we calculate the difference between the heights to calculate delta H, which will be H0 minus H1 Hi. So this would mean that it would be 20 minus 10 mm, and this would mean that it is 10 mm. When we have this, you can use got it. Where was I? Yes, so you can use this formula or this formula to calculate alpha, which is bite angle. Okay, can you do the simple calculation and tell me your results? Let me start a whiteboard. So the formula is alpha is equals to square root of delta H over R. So this is something which we have to calculate, which means that we have to assume this value. Let's assume this value as, let's say 10 mm, very small diameter, radius, which will mean that it has diameter is 20. And then if we make this calculation, we have 10 divided by 10 square root. What's the answer? It would be 1, right? One. And then using the formula on the next slide, using the formula on the next slide, so this formula we can calculate the friction coefficient, which would be required to do this. And when I do that, so 1 and 10 of 1. Oh, it is in degrees. Doing the same mistake. Okay, 1 and 10 of 1, it would be 1.55. So yeah, when I want to calculate friction coefficient required, and if I use 10 of alpha, which means 10(1), the result is 1.55. Remember, one is in radians. This is quite important. Okay, and then, for example, what we would want to do is we would want to change the value of R such that what we want to do is we want to change this value such that mu is less than equal to 0.2. That is the goal, and that is something which we want to play with. So can someone do this calculation and provide their results? Until now, what I would like to do is I would like to ask a question if the problem was clear. The problem which is stated here. that what we want to do is we want to calculate the roll radius. That's it for now. Okay, most of the students say that it is clear. If you're saying that it is not clear, I would like to know what you did not understand, and I would like to clarify it, because this is important for this lecture, which is basically focused on rolling, and also for the examinations, because there we would expect you to do these kind of calculations quickly. Again, if you're saying no, then I would like to know why, so that I can clarify it here. And if you're saying yes, what I would like you to do is to give a number on what this radius should be to satisfy our rolling conditions. Or let's do it again. What I would like to do is I would like to remove this. So now if I choose a radius which is relatively different, let's say we choose a very big radius, 100 millimeters, and now the equation becomes 10 over 100, and now we do the calculation. So alpha comes out to be 10 divided by 100. Square root is 0.316. 0.316. Again, this is in radians, not in degrees. And then we can use this function, mu is equals to tan of alpha, and then this can be still the friction coefficient is coming out to be 0.32, which is quite large, and we would like to bring it down below 0.2. This means that this is still too small for this kind of reduction in the material using the conditions which we have already given. Okay, we have to memorize all of the formulas for the examination. Very interesting question. We will answer it later. The answers which are coming out are 250 millimeters, 256 millimeters, 250 millimeters, 78 millimeters. Let's try it with 250 millimeters. Okay. Or what we can do is we can just okay. Conversely, what we can also do is we can use a direct equation by putting in the value of r and so on to calculate all these. So we have 10 over 250, and the answer comes out to be 0.2, and then mu is equals to tan of alpha, so tan of 0.2, and this would come out to be 0.2 precisely. That's great. This would come out to be 0.2, and yeah, so it can be yes, so it should be, for the conditions which we have provided, let's change the color, r should be greater than 250 or so on, so almost, and that is how we are calculating r. Interestingly, that's great. Now if you want to calculate the total strain in the material, how will we do that? Can you calculate that? It is quite easy. The formula for total strain in the material was total strain component is equals to log of h1 over h0, right? Yeah, so it is h0 over h1. So this is h0 over h1, and for this kind of rolling, if you calculate phi, can you calculate this log of 20 by 10? Can someone give an answer? 0.69. Super. So it is 0.69 or 69%. That is interesting. The next thing we realize from here is that it is quite difficult and quite cumbersome to do this process using worm rolling, because the radius and diameter of the roller would be then greater than 500 millimeters. So what we usually do with this kind of thickness reduction is we do it in multi-steps, because this would require a lot of force. Interestingly, we cannot do it specifically like this. So what we would like to do is we would like to do in multiple steps. So instead of doing all this reduction in one step, we would divide it in 2 or 3 steps and do it adequately. While doing this, let's go back to the slides. I want to know how much force is required to do this process. So what would be the rolling force? Now the formula for rolling force is quite interesting. Let me open it up. Can you find it in the slides? View, navigation panels, bookmarks. So I want to clean it up, but I want to keep this here and this here. So let's change these. Okay, so now we know our roll radius and we also know our total strain. Now we are interested in calculating the total force required. So the total force basically is depending on the total force is basically depending on several aspects. Let's see. Velocity, forward slip, backward slip, mean strain, no slip point, to calculate no slip point, and there is no calculation of force. Generally what we are doing is calculate the force required. What we are doing is we are using this simple formula of total force is equals to width of the roller, and then we are integrating the total force between all these points with roll pressure, which is this P, the length, and then let me write it separately, and then dl, where this length is the differential component of the length. So at each instantaneous length we are doing this calculation, and then we are summing it up to calculate total force. The simplified version of this can be written as the total force is equal to the flow stress multiplied by width multiplied by total L, where this is L. So if we know alpha and we know roll radius, we can calculate this value of L, which would be linear length. L is equals to R alpha, where alpha would be in radians, and so we can calculate that, and then from there we can assume the width of the sheet to be something, and then we want to get the flow stress component. So this flow stress component comes from the stress strain curves, which you have already studied. So if I go here, so generally what we were observing was that we are doing warm forming, so usually in this range. This is the curve for cold forming. This is the curve for warm forming of this material. This is the curve for hot forming of this material, where the melting temperature is 1200 degrees centigrades. And let me come back quickly. Okay, super. And from here, for example, if we have 0.69, which is almost here, strain in the material, the flow stress required to achieve this is somewhere here, and that is something which we need to plug in that equation and get our output for total force which will be required to do this process. But usually what is happening is that the force is not fixed. So this is L. From this point to this point I am moving here, and this is the force. So basically what is always happening is that this force is less here, increases, and then falls back at this point, and this point is called is usually in the neutral point, or the point where the force is maximum. This is where the speed of the roller is equal to the speed of the billet, and where there is only one component acting on the billet rather than two components, which is horizontal and vertical, and therefore the force is highest at this point. But when we are talking about the total force in the very simple equation which I showed you on the other side, which was let's say which was force is equals to YF, which is yield force multiplied by width multiplied by length, and this L is, let me define them specifically. So this L is grab length, this is width of the roller, and this is flow stress. Clear? And if I clear this all up, and just from remembering, we have roll radius which is equal to 250 mm, and we have phi which is 69% almost. What we can do is this grab length is something which we can calculate from L is equals to R alpha, and we know this alpha which is coming from the equation, simple equation of delta H over R, and this R is something which we already know, and then the width of the roller is something which should already be known, and then the flow stress is something which we are getting from stress strain curves or flow curves with respect to the strain which we have. In this case it is the 69%, as I said. So this is something which is quite interesting. These are some very basic few calculations which I feel that everybody should understand and be able to perform. If you have any questions, you can put them here. If you have generally understood what I have stated, you can just vote. If you have understood everything, you can straight vote true. If you haven't, you can state false. In the case of false, I would highly recommend that you put in your questions so I can answer them for helping you understand them better. Because this is something which we will use as a base in the next lecture and build on it. I will ask you to continue to vote. Meanwhile, what I have done is I have uploaded all the lectures for you which were recorded, which I want to share now. So if I stop sharing this and I start sharing this screen, so now you will be able to see this screen here. And in the lecture manuscripts, what I did today was I uploaded these slides here, and what I also did was I uploaded this in the recorded. I made a new folder, recorded lectures, and in this recorded lectures I uploaded this document. So basically they are not really recorded lectures, but we had recorded lectures which were of relatively bigger size. We could not upload all of them on Opal without compromising on the quality. So instead what we did was we uploaded them on YouTube and made them unlisted, so only the people with the link can see them. You can download this document, and in this document there are all the links to those videos. I would recommend that you open up this first link. So if I open up this link, it will open up this playlist which has all the lectures which are recorded. You will see that lecture 1 is missing, then there is 2, then 5, 8, 9, 10, 11. So probably after 8, 9, so after this we were able to fix things with our technical problems, and yeah, then we were able to record lectures. The lecture today will also be uploaded using in the same playlist, and you will be able to see it there as well. So now you have access to some of the recorded lectures which are there, and all the slides which are there, and all the topics which are there. Something else which I want to discuss is so generally that is it. If you have any questions, I will be happy to know. Can you send us some homework by email as PDF regarding this lecture? We'll visit in the next week. Can you send us some homework by email as PDF regarding to this lecture so we can discuss it in next week? I don't understand that. So what I will do is I will be uploading this recording on YouTube, and you can use this as an overall help or an overall document for understanding what the homework was and what you can do with it, or the data which we did and how did we calculate and things like this. Thank you so much for your efforts and record lectures. You're more than welcome. I'm sorry we were not able to record all the lectures, but yeah, hopefully in the future. And yeah, so generally here we are at the end. What I do is I see that when we are in the lecture, so for example, now we have almost 30 students who are participating in the lecture, and almost 15, 16 who are actively participating in the polls and everything. So I would see, I would say that almost 17 students are actively participating in the lectures, but the number of students who registered for the examination is almost 95, and I don't know the reason how and why. Can somebody explain that to me? And then one student has a question regarding VF is greater than VR is greater than V naught. Yes, we can talk about it at the end. What I will do is I will clear up this board for answering that question. So in case if nobody has a question, and if you're not interested in knowing VF is greater than VR is greater than V naught, then Thank you very much. The lecture is over. See you hopefully next week. So, Mr. Parmar, are you with me here now? We want to discuss this thing with VF, VR, and V0. Specifically, I would like to know what is your specific question, which you already mentioned above, which was, I couldn't get, could you please repeat it? What were you not able to get with this topic? I would like to know. And if you're comfortable, you can also open your mic and speak rather than typing, which would be more quick. Yeah. Hmm. Hmm. Okay. So your question is basically why these two velocities are different. Okay. Um, Quite plausible and quite understandable. So let's say we have a billet of this size. It has a specific height, it has a specific length, or I will write this length as L, and it has a specific breadth, so we will call it width. And now these are initial values. Okay, and now when we are rolling it, we are getting the final shape is something like this. This would mean that now the height has changed, the length has changed, but the width we kept it fixed, so it is still constant. So W0 is equals to WF. So far so good. So we see that the initial block is more in height, less in length. The final billet is less in height, more in length. And what is happening here is that the volume is same. That is the basic reason why this equation is true. So far so good. Super. Now, considering that the width is fixed, we want to remove this component from here, and the process would be happening in some infinitesimal time, so it would be happening in a certain value of time. So basically what I'm doing is I want to convert this easily into non-length dependent function, so I'm dividing it both with time. Now just to keep it simple, it's not, now this is velocity, the initial velocity, and this is final velocity. And by these velocities I mean that the total length divided by the time in which this length would pass through the rollers, and by this I mean the total length versus the time by which it will pass through the rollers. Now the process is continuous. This means that this is going in and this is coming out of the rolling mill. So this would mean that the time for both is same, and this would mean that the time required to the total velocity of this side would be lower, because this will need low velocity to go from point A to point B, will require so it is easier to show it with the equations. So the velocity of this would be slower and velocity of this would be higher, because it has to quickly pass through the rollers and it has to slowly pass through the rollers. So what is happening here is that it was easier to show with the equation, with this equation, that this h naught is large and this hf is small. You can see it from here. So this h naught is large and this hf is small, clearly. And this would mean that when there is an equal sign in the middle, automatically this would mean that this has to be small and this has to be large to satisfy this equation. So far so good? Okay. And when we are building a rolling process, so let me clear everything up on the top. Okay, so when we are making our rolling process, I will only make half of it, so it is easier to understand. Let's say it is like this. Now, so this means that this velocity v naught is low, and this velocity here vf is fast. Okay, and when this material is moving in slowly and this material is going out faster, what is happening is that the velocity is changing throughout this grab angle. If I plot it like this, alpha, so the velocity is fixed before this line, velocity is fixed after this line, but it is changing from this slow velocity to high velocity throughout this line. Is it clear? And now comes the other thing. So we are using rollers, so these rollers have their own velocity, and then I gave the formula of how to calculate that velocity, but that is VR, and that velocity is fixed. So the rollers are rotating with a fixed velocity, so this surface has its own velocity, the roll surface, but the velocity of the material which is in contact with the roller is changing. It is different at this point, it is different at this point, and it is varying in the middle. So there comes a point, not precisely in the middle, but relatively on the initial side, where the velocity of the material and the velocity of the roller is same, but before this point the velocity of the roller is faster and the material is slower, and after this point the velocity of the roller is slower and the material is faster. So here the material is flowing faster and here the material is flowing slower. On the other side, let me use different arrows. On this side the roller is moving slowly, and here the roller is moving fastly. Is that clear? So now what would happen is that because we are rubbing one surface on the other on this end in the beginning, we are rubbing a faster surface on the slower surface. So this would automatically pull this billet inside. And on the other side, the material is going faster and the roller is slower. So this would automatically pull this material in. So here the overall force on the material would be negative, and here the overall force on the material would be bigger. And now what we want to have is we want to have this force intake and force out, which were here. We would like this force to be always bigger than this force, and only then we can continue rolling. Otherwise the material will not be able to, we will not be able to roll the material. So that is how the velocities interplay, and now that is why the velocities are changing, because of the geometry of the billet which is going through the rolls. Is that clear, or I made it more complicated? I don't know. You cannot understand that? It is quite simple to understand, because what we are doing is we are always, during the rolling process, we are always reducing the thickness of the sheet. So when you're reducing the thickness, you have to increase the length to keep the volumes fixed. So we are, in the rolling process, we are never increasing the thickness of the sheet. We are always reducing it. So the length will always increase. And when the length is increasing in this area, the velocity of the sheet on the exit will always be greater than the velocity of the sheet at the inlet, due to the overall intrinsic attribute of the rolling process that we are reducing thickness of the sheet. Super. Now we have another question. How can we divide the thickness change in different rolls? As you said, we cannot deform that much thickness in a single roll. Okay, interesting. So I would like to point that out here as well. So let's do that quickly. What I said was that we have initial roll so the material is going out like this. So initially, for example, we have 20 millimeters and we want to get a sheet in 5 millimeter thickness. Okay. Now this is just as an example. So when we will see that we have to reduce 15 millimeters of thickness, which is quite much. And if I calculate the overall strain, which will be, strain is equals to log of h0 over h1. So then it would be 20 by 5 log, and it would be quite a humongous number. Then what we want to do is, instead of doing this completely, what we want to do is we want to reduce and we want to decrease it in steps. So what we can do is we can reduce this 20 millimeter to let's say 12 millimeters, and this 12 millimeters to 8 millimeters, and this 8 millimeters to 5 millimeters. Okay. So instead of going through a lot of deformation, for example, in this case, it would be 20 divided by 5, and I don't know, log of So it would be 138%, which is quite high. I can do this, which is 20 divided by 12, which is 50%, almost 51%. And then I can do this. This is almost 40%, and then this is almost 47%. So overall, we are getting this reduction, but step by step. And then it is easier to or the rulers would be inadequate size, and the process would be such that the friction coefficient would not exceed the actual friction coefficient which is present there, and we will have a grabbing condition and we will be able to roll it. So that is how we do multi-step rolling to achieve our required thicknesses, from very large thickness to a very small fine thickness. But yeah, keep all the conditions fixed. Okay. So if we have no further questions, then I would like to end up this lecture. Thank you very much for your time and your consideration, your focus, and we will meet in the next and the final lecture. But please do these calculations, and if you have any questions, write them down, and so on, so we can discuss on them next week. Thank you very much. Bye.